Okay, let's start then. We will continue with the discussion of the basically statistical properties of the linear model. So if you recall again, we had the linear model, and then we had assumptions, a bunch of assumptions. So there was the E1 assumption where we assumed that these are statistical assumptions about the noise. The noise is zero mean. It has covariance, the squared identity, and then there was the E2 assumption, where we further assume that the noise has a multivariate normal distribution with mean zero, covariance sigma squared IN. So this E2 is stronger than E1. So E2 implies E1, but not vice versa. And from E2, we got that, for example, Y is normal with mean zero. That's not correct. Let's call this mu, x beta mu. So the mean would be mu. Covariance matrix would be sigma squared IN. And this allows us to basically, let's say, get this distribution of beta hats. And also the residuals and a couple other things that you can get from this. Yeah, E1 just implies, so this E1, so this is E2. So under E2, that happens. Under E1, we just get that expectation of Y is mu, and the covariance of Y is sigma squared IN, but we don't get that distributional result. So that's all we get. Okay. So there was another assumption as well. We did it early on, x1. So it's an assumption about the x. X has whole column rank. Anyone remembers where this was used? What is the significance of this assumption? Yeah, so linear, so the columns of X are linearly independent, but what was the significance? Yes. That's actually a good point. Covariance matrix of what quantity? So actually we can prove that the covariance matrix of anything is positive semi-definite with no assumption. Yeah.
Invertible.
Sorry?
Invertible.
What is invertible?
So X transpose.
Okay, yeah. So the consequence is like X transpose X is invertible. Okay. If and only if, and the consequence of a positive sense. So it's so we can conclude that X transpose X is this we talked about is positive definite. Okay, not positive semi-definite, but positive definite. Okay. Positive definite means a little more sense. So this turns out to be a good place. I'm going to go over these a little more carefully below. So X transpose X is going to be always positive semi-definite, but it's going to be positive definite if and only if X has full column rank. I'll get to this. If you don't remember what it is, becomes clear. There was another statistical consequence, like a key statistical feature of this. Anyone remembers?
Identifiable.
What is identifiable?
Beta.
Beta is identifiable. Okay, great. So from this assumption, we get that beta is identifiable in the linear model. In the linear model, the model above. And for example, implies also that beta hat is well defined. The least squares estimate is well defined. So beta hat is the least squares estimate. Otherwise, the projection, which is mu hat, is well defined always. But you could potentially write it in different ways in terms of the columns of X. So you couldn't identify a single beta hat. So for the estimator to be well defined so that we can talk about its properties, this was needed. So if you go back, you got the normal equations, and if this condition holds, X transpose is, so X transpose X is invertible, and then we can solve uniquely for beta. So this expression that we got, beta hat is X transpose X inverse, only makes sense if X transpose X is invertible, which would be under this condition. And in fact, these are equivalent. So that's what I want to like spend a little bit of time arguing these directions, because we just mentioned it. It's a good like time when you wrap up this part of the course to just so that you fully see everything. So let's work on this matrix, like talk about this matrix a little bit. So we have, let's say, let me write X in terms of its columns. So X naught, X1 up to XP, these are the columns of X. So you get n by p plus 1 matrix. Each one of them is a p plus 1 by 1 vector. And then when I form the X transpose X, what can I say about the elements of this in terms of the columns of capital X, in terms of the Xj? What can I say about the Xij? Yes. Dot product, yes. The pairwise dot product or inner product. Yes. So Xi transpose Xj or the inner product Xi Xj. So remember this one, and you can also like prove it rather quickly. You transpose, you get this, and then you keep the other one, so it has to be 0. And then you multiply as if you're multiplying scalars because the dimensions match. So the first element will be x naught transpose x naught, and then you multiply by x1, and so on. Okay. I'll be very brief here because I hope you know. So you multiply out. Yes, was that
This is
question?
a notation just to IJ, just doing the dividing numbers.
Can you say it a little bit louder? So
No, no,
what?
I understand this.
Okay. So the notation is clear. So this is like these are column vectors. So Xi transpose Xj is a scalar, and this is also the inner product. We can call it the dot product. Okay. So for this reason, this is called a Gram matrix in linear algebra. It's just a matrix that collects all these pairwise inner products between a collection of matrices. So it records the pairwise inner product of columns of X, called the Gram matrix of the set of vectors. And the properties are that this is always symmetric and always positive semi-definite. Okay, so it can serve as like the covariance matrix in general. And its inverse can also serve as a covariance matrix because that would be positive semi-definite. So the way to prove it, so anyone remembers what the positive semi-definite means? Yes.
It's like if the determinant was greater than equal to 0. The positive definite is when it's always greater.
That's not equivalent. So a positive semi-definite matrix has a determinant which is greater than or equal to 0, but that may fail. Yes.
The inner product of x and ax greater than equal to 0. Oh,
X, okay, so I'm going to use U. So U, you have a matrix A. Inner product of U and AU is greater than or equal to 0 for all U, for all vector U. Or you can say U transpose AU is greater than or equal to 0. Okay. That's the definition, right? Which implies that all the eigenvalues are non-negative, which then implies that the determinant is non-negative because it's the product of the eigenvalues, but potentially you could have like 2 eigenvalues that are negative and the rest are positive, and the product will still be non-negative. Whereas it's not going to be a definite matrix. Okay, so if I want to prove that this is positive semi-definite, I'm going to use the definition. U transpose X, transpose X U, that's the middle A. And so what I get is I can rearrange the parentheses. So you get U transpose X transpose. I'm going to put the parentheses here and then XU. So what happens to the first? What kind of simplification you can make? Yes.
I take the transpose, make it U x transpose.
XU transpose, yes. So that would be, if you transpose, you have to switch the order. Okay, so you get XU transpose XU, So it's a vector xu times its transpose of it times itself. So it's really the norm of xu. So we get this. And the norm is always non-negative. Okay, so this proves that this matrix is positive semi-definite because when you form U transpose that matrix U, it's always non-negative because it's the squared norm of a vector, which has to be non-negative. Okay? So this is proof, and then so the eigenvalues are always going to be non-negative. And if the columns are orthogonal, then it would be diagonal. This is kind of obvious because these are inner products, all the off-diagonal elements would be zero. And if the columns are orthonormal, which means that moreover, in addition to the previous statement, the norms of individual vectors are also one. So you have a unit norm, then the diagonals will also be all ones, and so this matrix would be identity. Okay, so under the assumption that the columns are orthonormal, we get that simplification. Under just orthogonality of the columns, you get the X transpose X is diagonal. Okay, so these are some facts you can derive from the form of X transpose X and also the fact that it's related to, or just basically captures all the pairwise in mathematics. The normal part here is, yeah, I think like xj is norm is equal to 1. So far, so good. Okay, now, when can we say that X transpose X is positive definite? Just going back to that statement. Yes.
The inequality is strict.
Where the inequality is strict for, so if U is not equal to 0, then U transpose XU is strictly positive. Because for U equals 0, it's always 0. But if this is strictly positive, whenever U is non-zero, then this is called the PD or positive positive definite matrix. And so what condition do we need for that? So this matrix is always positive semi-definite, but it's not always positive definite. How can I guarantee that that happens? Yeah.
Full rank. X is full rank.
Yes, why?
Because then X transpose X is full
Yeah, these are all correct statements, but doesn't get to so why does that imply what I want? So you want this to prevent this from becoming 0. Okay. So this would be 0, U transpose XU is 0 if and only if, because it's equal to the norm squared, if and only if norm of XU squared is 0, right? But the norm of a vector is 0 if and only if the vector itself is 0. So what does this mean? Yes.
That means there's a null space. The U is the null space.
Yeah, so U belongs to the null space, or U belongs to the kernel of X.
If X does not have a null space, that it's full rank and have these.
Okay, we have to correct that. Like every matrix always has a null space, but the null
yeah,
space could be yes. So the null space could be trivial, which means that. Okay. So if kernel of X is trivial, like i.e. equal just to the 0 vector, then we can conclude that U is we can conclude that XU is non-zero for U that is not 0, and so the matrix will be positive semi-definite. Sorry, positive definite. Okay, so the condition is equal to the condition for this to be positive definite is the same as the kernel of X being trivial. And the kernel of X being trivial means it's full rank. Okay, because of the rank OIT result. Okay, so this is equivalent to the kernel of X being trivial or equal to just the bare minimum, which is the set containing 0. And so if that's the case, then it means that whenever U is non-zero, XU can't be 0. because otherwise that non-zero vector would be in the kernel, but we're assuming it's not. So this condition, these are all equivalent to basically xt being. Yeah, I mean, you can like correct the statements, but this is equivalent to x transpose x being PD. So x transpose x is quasi definite if the kernel of x is trivial, which is equivalent to the x being full rank. Yes.
Definition of a kernel being trivial is just it having the zero.
Yes, yes, yes. I mean, I could have just written this. Yes.
Oh, that's it. Okay, because I saw IE, so I was like wondering if the
IE means like that is.
okay, I was like curious if trivial included anything other than just zero.
Yeah, that was a maybe not the best choice of expression. So that's kernel x3 means kernel x. Okay. So another manifestation, we're going to do it a different way, which is related to just that, what we did there. So I'm going to prove that the rank of x transpose x is equal to the rank of x, which we kind of already did, but then we do it formally. And then you can see that if the x is full rank, then x transpose x is full rank, which means that a full rank square matrix is always positive definite. It's like invertible. So this is another way of like clean way of doing it. So in order for us to show this is the result that we wanted. So we want to show that if x is full rank, then x transpose x is invertible. So this result allows me to do that. So it suffices to show that the kernel of x and the kernel of x transpose x are the same. We just actually did it, but I'm going to do it a little bit more cleanly here. So this is enough because when this is full rank, we'll have kernel 0 by rank nullity, and then the kernel of this would be 0, which means that it would be also full rank. So by rank nullity, kernel of x trans, so the dimension basically of this, the dimension of the image, rank of x transpose x, plus the nullity of x transpose x is going to be p plus 1. It's a p plus 1 by plus 1 matrix. So if this is 0, then the rank would be equal to p plus 1. And so if I can show this, the same goes for this. So kernel of rank of x plus the nullity of sorry. Yeah, so let's not write that. That's going to be a little more tricky. So kernel of x transpose, this is going to be enough to argue for yourself. The kernel of x transpose being equal to kernel of x is enough for the rank of x transpose x is equal to rank of x. So this is true because I'm going to show that the two sets are the same. So if xu is equal to 0, then I multiply both sides by x transpose. I get x transpose xu is equal to x transpose 0 equal to 0. So this implies that u is in the kernel of x transpose x. Okay, so this initial statement is saying u is in the kernel of x, and we conclude that u is in the kernel of x transpose. So this first statement means kernel of basically x transpose x contains kernel of x. Anything that's in the kernel of x ends up in the kernel of x transpose. The kernel of x transpose x includes is a superset of kernel x. On the other hand, if I assume that something is in the kernel of x transpose x, then that holds, then I multiply by u transpose to get this. Right. And then this is equivalent to this, and then this is equivalent to that. So u belongs to the kernel of x. So this is a more direct way, like a formal proof. sorry, just let me finish this. Then this second statement is just saying kernel of X transpose X is inside kernel of X. So two sets that are each subsets of the other have to be equal. Yes.
For I saw the kernel equation, I saw like X and U, I guess, following, and then U is how you determine the space of the kernel. For the second statement where you X transpose X, U, are you able to just put, does the order where you put U not matter definition? Because I see you put U transpose to find the space of.
This is the definition. So U belongs to the kernel of X transpose X, that whole.
Oh yeah, that's the definition.
Right. Then I multiply by U transpose, then I make a conclusion. Okay. And this is the definition of the U being in the kernel of X. So start from a definition of U belonging to one of these, and then you conclude that it belongs to the other. Okay. So it's like a basically this argument that I did here, just a little bit more carefully. So this in particular shows that, any questions about this? We did it like twice, and the second time a little more carefully. But the argument is very simple, I can see, like X transpose X being invertible, which means it is equivalent to itself being full rank, is equivalent to X being full rank, having full column rank, and it's equivalent to columns of X being linear independent. And all of it is also, as we have shown, is equivalent to X transpose X being positive definite. And so these statements are all equivalent. And just roughly follows from the fact that this identity holds, basically. This very basic identity. Okay, everything kind of follows from this manipulation. Okay, so far so good. So this closes one of the gaps that we kind of waved our hands around. That you can formally prove, and you get a lot of properties of X transpose X for free. Any questions? Okay. Let's move on. The second thing that I want to talk about a little bit is, again, recall that we had this hat matrix. X transpose X inverse, X transpose. So what was this hat matrix? What? Yes.
It's orthogonal matrix.
Orthogonal projection matrix. It's not an orthogonal matrix per se, but orthogonal projection matrix. So what does it mean? Again, the picture, you have the image of X, let's say. You have Y. So what does the edge do? Yes.
It just projects Y to the.
So if I apply edge to Y, I get HY, which is going to be the projection of Y. We call this mu hat, like their fitted values and regression. And then the residual I can write as I minus H times Y. Again, Y has this decomposition, HY plus I minus HY. This belongs to the image of X. This belongs to the image of X perp. Okay. Mu hat E, and this is an orthogonal decomposition of the space. Every vector has these two components. Okay, H happens to be the operator or matrix that projects onto the image of X, and it turns out that I minus H is also a projection operator that projects into the image of X perf. Okay, I minus H is also an orthogonal projection matrix. Projects onto image of X perp. Why this is true? Because if you imagine, if you claim that this is the projection, let's say E is the projection of Y onto the image of X perp, in order to prove it, I have to show that the residual of that projection is orthogonal to that subspace. So the residual of that projection is really mu hat because that's y minus e. This is the residual of that projection, and mu hat belongs to the orthogonal complement of this because the orthogonal complement is the set itself. So mu hat belongs to the image of x, which is in the orthogonal complement of the orthogonal complement of the image of x. So that's the proof that E is also the projection of y onto the orthogonal complement. You just argue from orthogonality of the residual to the corresponding subspace. Okay, so this is an orthogonal projection matrix. It has the properties of orthogonal projection. It's symmetric and idempotent, just like H is symmetric and idempotent. You can prove it algebraically from the properties of H. You can prove it from this result, like just a formula, or you can use the geometry, because geometrically it's projecting onto here, like visually the orthogonal complement would be like this kind of line if this is the origin. And so applying IH is projecting onto this line. And so you get these two components, one in the image of the other in the orthogonal complement. Okay, so far nothing kind of new. Any questions? Okay, from this, the point is I can use these because I have written mu hat as a function of y, like a linear function of y, as well as the residual. I can use the properties like linearity of expectation and properties of covariance matrices, how it operates on linear transformations of vectors to drive the statistical properties of mu hat and residual. So for example, I can ask under E1, if you remember, under E1, which was saying mu is, let's say, has expectation x beta, which is mu, and covariance sigma squared I. So under this, what is the expectation of, for example, mu hat? Can we use that result, hy in projection to drive this? Anyone? Yes.
Just
Yeah, but we need a little more details, maybe like what is. Now, just maybe we can go ahead. Like, how do you prove it? It's mu.
you take the linearity of expectation, you take each other.
Right? Yes.
We know the expectation of y is just
Right. So I get h mu. And then y this is equal to mu. There's both like an algebraic reason and a geometric reason. Yeah, maybe let me just see if you have like an idea.
No, I it was like if
Okay.
I just expressed mu in terms of x beta and then h in terms of x, like all of that, then the middle part cancels out.
So multiplying h by mu, the x transpose x cancels the other one,
And then you're left with x beta.
x beta. Yes. So this is the algebraic way. So you just write down everything, just cancel everything. So what is the geometric way? Yeah, okay, so
Well, mu's in the image of x, we project it, or basically it's already in the image, so which nothing.
great, yes. So that's the geometric idea. So mu is somewhere in the image, and h is trying to project it onto the image. It's already there, so the projection is going to be itself, because the error is already zero. So you don't need to do calculation if you kind of understand the geometry. This has to be mu. But the good thing about linear algebra is that like both sides can agree. Everyone sees it, mu is in the image, so I'm going to try to project it again, so it's going to be itself. So how about this? Let's do also this, just fun. Expectation of E, which is the expectation of I minus H times Y. I can again pull out I minus H. and then this is mu. So I get I minus h times mu. So what is this guy?
Zero.
0. Why is it 0?
So I moved the mu into the associated into the yeah.
We can do this, like expand, you get mu minus h mu, and h mu is equal to mu. There's also a shortcut. You don't really need to do this because I know that I minus h is projecting onto the orthogonal of the image of x, and mu is in the image, so it has no component in the orthogonal direction. So anything in the image of x is going to be killed by I minus h. So no matter what I get here, like anything in the image of x, if I apply I minus h2, it's going to give me 0 because it has no component in the orthogonal direction. And this is trying to project. So anything here, as I project, it's going to project onto 0 because, I mean, you can write it from the principal orthogonality. It's like that vector would be its error of projection because it's already orthogonal to the image of x per. So it is itself is the error, so the projection would be 0. Okay, this is even shorter, but this is also short enough. Okay, so the expectation of the residuals is 0. This is an interesting like fact that you get from orthogonality projection, added a bit of statistical assumption that translates into expectation being 0. Okay. And a lot of these orthogonality facts or principles from linear algebra translate into interesting statistical properties under these assumptions, as we'll see. And then mu hat is kind of unbiased in the language of statistics for mu. So if you want to estimate mu hat is an unbiased estimator. Okay, for that mean vector. As beta hat was unbiased for estimating betas. Questions? So this so far, I think all of you essentially have been able to do. There's nothing new here. We used what we knew before. And then I can easily calculate the covariances as well. I'll let you do it. These are just, again, the consequence of this result. Covariance of AY is A, covariance of YA transpose. A being either H or I minus H, you plug in and then use the symmetry and idempotence projections, and you get these results. And this one, I actually did it last time rather quickly, but as an exercise, do it. So covariance of E is not multiple identity, as opposed to the covariance of the actual errors, which we assume to be identity. These are under the E1 assumption. And so in particular, the diagonals of the covariance matrix of E are the variances of the elements. And these are basically diagonal elements of this. So 1 minus HII times sigma squared. And you can see that the variances are not equal, despite the fact that we assume the actual errors have equal variances. The residuals turn out to have equal variances, and just the fact that you drive. And this HII here is called the leverage score or leverage of observation I, and it would be a very interesting object later on when we talk about diagnostics. It's a measure of how much influence that observation exerts on the fit. Okay, if I just remove that observation, how much the regression, let's say in the simple linear regression, how much the regression line changes. And it appears elsewhere, like here in the visual variances as well. Just have that in mind. These are important quantities statistically speaking. Okay. So far, so good. Again, nothing new here. And then the expectations we calculated. So expectation of mu hat is mu, expectation of E is 0. And these are consequences of the fact that the mu belongs to X, the image of X as part of our linear model assumption. Okay, what I want to do next is, again, not new, but maybe first, statistically interesting. Second, I'll talk about cross-covariance matrix, which wasn't probably discussed very explicitly. We have seen it in the homework problem. So the idea is that I can do more in the sense that I can now combine, for example, beta hat and E. I can put them together in a vector and ask what is the distribution of this quantity? What is the covariance of this new vector? Okay, it allows me to study the joint behavior of beta hat and E. And it's important for us for reasons that we'll see. So this E is n by 1, and this beta is p plus 1, so I have a big vector, p plus 1 by n. And if you look at it, beta hat is ay, where a is this quantity. That X transpose, X transpose, we have called a, just for simplicity, and E is I minus hy. I can pull out y, and I get this expression. Okay, the reason why I can do this is p plus 1 by p plus 1, and this is n. Sorry, this p plus 1 by n, really. The A matrix is not square, and this part is n by n, and this y is n by 1. So the inner dimensions match. So if you imagine this multiply row-wise, the first row will be the first row and multiply by y, up until when you get to the last row a times y. So you get this top block, and then you can argue row-wise again. And so you get this, when you have this partition, you can pull out y, you get this. If you haven't seen this, it's a very good exercise. You try to argue for yourself that this can be written as a times minus hy. And then I'm going to call this matrix P. And so we have another instance that we have a linear transformation of y, now from n to a bigger space. But that's fine, it's still a linear transformation. Okay. And I can apply the things that we know about linear transformations. So I can ask what is the expectation. In particular, I'm going to ask what is the covariance. What is the covariance matrix of beta hat E? And it's just the covariance of Py. And I hope everyone knows this is going to be P covariance of Y P transpose. Covariance of Y is sigma squared I. And so I get sigma squared I. I goes away. I get P transpose. Okay, and then I expand. P is A I minus H. Here I get A transpose I minus H transpose. And then I multiply clockwise. I can multiply this by that. The dimensions again match. You can verify you get A transpose. It's as if I'm multiplying the 2 by 1 by 1 by 2 vector. What happens to be blocks here? So I times I minus H transpose, I minus H times A transpose, and then I minus H times I minus H transpose. Okay. And at this point, some simplifications happen. Oh, there's a sigma squared as well, which I forgot. It's going to be sigma squared here. So for example, this block is going to simplify. So is this kind of multiplication kind of clear? So you do the transpose of this, and you transpose each block, and then you also change the kind of layout. Right? It's as if you're transposing a vector, but these are blocks, so they themselves get transposed. And so if I have A, B block partition, if I do the transpose, I get A transpose, B transpose. Okay, and then you multiply here blockwise, and then you get like 4 blocks. These are not like scalars, but because the inner dimensions here, so this matches this dimension, you just multiply, and this matches this dimension, you can multiply. Okay, questions? Do we have any simplifications here? Yes.
Can you make the bottom, H1?
Yeah, so I minus H transpose, this is equal to itself. And then I get I minus H squared, which is still equal to itself. So this is, by symmetry and idempotence, this is going to be I minus H. Okay, and this also happens to be A times I minus H, for example, by symmetry. So these simplifications happen. And in particular, if I write it down, I get sigma squared A transpose, sigma squared AI minus H, sigma squared I minus H A transpose, sigma squared I minus H. So the reason why I did this exercise are twofold. One is to note that a couple of things I already knew I didn't need to calculate. For example, this guy, what is this, the covariance of? Covariance of E. And the reason why it's a covariance of E is not because we remember the form, because when you do this block partitioning, the covariance matrix will have these blocks. I'm going to write it as covariance of beta hat and beta hat. I'll tell you what this means. Covariance of beta hat and E, covariance of beta hat. Like E and beta hats. And then covariance of E and E. So these are cross covariances of two vectors. And so what does a cross covariance mean? So if I have two vectors, Y and Z, the cross covariance is just similar to the covariance matrix that we defined. So Y minus the expectation of Y. And then times Z minus the expectation of Z. And then I take the product, but this has to be transposed because this is a vector. So this is a more general version of if I do covariance of Y and Y, I get that covariance matrix that we had. Y minus the expectation of Y, and then Y minus the expectation of Y transpose. Okay, so this I used to write as, or I still write as covariance of Y. So cross covariance of a vector with itself is really the covariance matrix. This is a slight generalization, which you have hopefully seen in homework 3. And this can be not a square. So if Y and Z have different dimensions, this would be a dimension would be dimension of Y by dimension of Z. And it's not necessarily symmetric. In fact, covariance of YZ, covariance, for example, this is going to be the transpose of this. So cross covariances, when you switch the order, it will be transpose. This guy is going to be symmetric because once you switch, it's going to be transpose, but transpose of itself, so it's a symmetry. So this is really going to be covariance of beta hat, and this is going to be covariance of E. So when you do this block partitioning, whatever happens in this 2x2 block would be the covariance of E, and it matches what we calculated before. This one would be the covariance matrix of beta hat, which if you calculate like A times A transpose simplifies to, hopefully you remember what the covariance of beta hat is. What is the covariance of beta hat? Sigma squared X transpose X inverse. So this will simplify to that. So this would give you the same information. The only new thing that we have discovered here is this block, which is going to be the covariance of beta hat and E. And this is going to be the transpose of it. It will be the cross covariance of E and beta hat. So that off-diagonal block is of interest to us, okay? That's what we got, rather, out of this calculation, in addition to what we had before. Is this kind of clear? So if I only wanted this block, I didn't need to do this full calculation. I could just calculate this directly, and I want to maybe do it here very briefly. So the rule for pulling out linear operators is similar. Remove this. It's going to be covariance of Y. So the rule here is going to be similar. So if I do covariance of, let's say, beta hat E, if I wanted to do it directly, I have that this is equal to the covariance of AY and then I minus HY. Okay, I just replace beta hat and E by the formulas that we have there. And then I pull A on this side and the other matrix on the other side, but once I pull it on the other side, it gets transposed. So I get A times covariance of Y, and then Y, and then I minus H transpose. So this matrix, when it comes out on the other side, it gets transposed. It's very similar to the idea that we had A covariance of Y, A transpose. This is a more general version, and it just follows from this formula. If you plug it into that formula, you'd see that this happens. So I would prove that this is equal to this. Covariance of Y and Y is just covariance of Y. So this is going to be sigma squared I. And this is going to be I minus H transpose. So I have sigma squared A I minus H transpose, which is the same as what I had before. So this is the same as this. And then you also get a simplification that the transpose goes away in this case, but in general, you get that. So if you have two vectors of, let's say, AY times BZ, you get A of Y Z B transpose. Okay, this is the general rule. And if you specialize it to the case where Z, so B is equal to A and Z is equal to Y, you get back the usual formula that we had. Okay, so these are not things that you need to necessarily remember, but you get used to it. And once you kind of understand, go back and understand where this ideal is coming from, the covariance of AY is A covariance of YA transpose, you see that this is like exactly the same idea, just a little bit more general. Okay, I'm gonna maybe zoom out. That was a lot of information, but really not too much. It's just, I just wanted to point out that there is this notion of cross covariance, and when you do the covariance of it, like a block partition matrix, you get these blocks. The diagonal blocks would be these covariance matrices, the off diagonals are the cross covariance matrices. So we did it in this case. The two diagonal blocks we already knew. The off diagonal block we got for free, and we could have gotten this off diagonal block in a different way, not different way, but just a more direct way. If that's all the information that we wanted, we would have directly used. Basically, this is the bilinearity of covariance, cross covariance operating. So you pull out the linear terms, but the second argument, because it's transposed, it just comes out on the other side transpose. Okay, I'll let you stare at it a little bit. Does this make sense? Was it too fast? Questions? So I'll let you figure out the cross covariance, but just the idea, the simple idea is this part didn't require any new idea. So we calculated the covariance beta hat E as a vector. It turned out to be that. And the simplifications are exactly because, I mean, the AA transpose is X transpose X inverse. That was lecture 6. And I minus H times I minus H transpose is I minus H. So the simplification is because of the I minus H being an orthogonal projection matrix. All we need is this new block. Okay, so this new block, which is A times I minus H. I need to figure out what this is. Okay, and then again, we can do this two ways, algebraically and geometrically. Okay, so let's do it. Maybe again, stop. Was this like, okay, maybe I'll show you this. This is how you do it. So you write it as P times Y, and then this is gonna be okay without any cross covariance kind of idea. So you get this, and then we want to figure out this quantity. Okay, and to figure out that quantity, I'm just gonna write it down. So remind you what this is. So H is X transpose X inverse X transpose, And I've called this part A, so really H is X times A. Okay, and so then I'm gonna try like to write it down. So I get A times I minus H, I get A minus AH. And so let's look at the AH. So AH would be, I'm gonna replace H with XA, and then replace, like just switch the parentheses. I get A times X times A, and A times X is, what is A times X? So that's A, when I multiply by X, I get X transpose X inverse times X transpose X, it goes away, like identity. So this becomes identity, I get A. And so when you do AH, you get back A, and so A minus AH would be 0. Okay, this is not very deep, you just write down the algebra. I just simplified by calling this piece A. If you don't like it, you just write everything down and try to cancel terms, and then you get 0. Okay. But as we have seen, zeros usually have like some kind of a geometric interpretation in this course. I want to maybe spend just 2 minutes talking about the like geometric interpretation, why this is 0 and from a geometric way, and it's much easier and nicer to understand. So I'm going to look at A transpose, and if you look at A transpose, that's gonna, let me do it here because I have A. So A is X transpose X inverse X transpose. I'm gonna look at A transpose. It's gonna be X times X transpose X inverse. Switch the order and then transpose. The second term is symmetric, so you don't have to worry. So I'm gonna call this D. So you get X times D, where D is invertible. So whenever you have something like this, X times a matrix on whatever side this is, let's say on the right, you can multiply column-wise if you remember matrix multiplication. So the first column of this matrix would be the first, you look at the first column of D, that first column gives you the linear, like coefficients of a linear combination of the columns of X. So that would give me the first column of the result. So if I write, let's say D as the first column, the second column up to, this is going to be P by P. So this is going to give me, it's like the inverse of the grand matrix. So this is going to give me P plus 1 columns. So the columns of the result would be really X times D0, X times D1, all the way to X times dP. And each one of them is like a linear combination of the columns of X. So this is like X beta, remember? So each one of the columns is in the image of X. Okay. Each column of the result is in the image of X. And so any linear combination of the columns, again, is in the image because the image is like a linear subspace, okay? So the point is that the image of this XD is going to be a subspace of the image of X. Because every column is in the image of X. And so any linear combination would be in the image of X. And in fact, it's going to be equal if D is invertible, and I let you, that this equality would be true because of D being invertible, but I let you like argue that. We don't need that. Okay, so I just need to know that the image of this, or at least every column, that's all I need. Every column is in the image. So if I now apply I minus H to A transpose, I'm applying I minus H to any one of these columns. Okay. So I'm going to apply this to XD, where you can see I minus H times XD0 all the way to XDP. So this is in the image, and this kills anything in the image. I minus H kills any vector in the image, so this is going to be 0. And every column would be 0 because every column is in the image, so the whole thing is going to be 0. So a 0 matrix. Okay. Again, the simple thing is that XD, the columns are in the image, and I minus H kills anything in the image. So when I multiply, the whole matrix going to get basically killed, or like 0. Does that make sense? So once you understand this columns live in the image of X, and then the I minus H applies column-wise, kills every column. That's gonna be it. So this is 0, and so its transpose is also 0. So we prove that I minus H transpose is 0 because I minus H projects onto the image of X perp, killing anything in the image. So this is 0, so the transpose is also 0. Transpose is what we want. If you transpose, you get A times I minus H transpose, but I minus H transpose is itself. So this is geometric interpretation of that result. Sounds good? Okay. So however you argue, you end up with this covariance of beta hat and E is that matrix. So the top block is the covariance matrix of beta hat, the bottom block, like the diagonal block, the covariance of E, and that 0 term is really the cross covariance of beta hat and E, and so we prove that they're uncorrelated. Okay, so that's the statistical content of this result, that beta hat and the residual are uncorrelated. So if you go to the next slide, under E1, which gives me the assumptions to drive the covariance matrix, covariance of beta hat and E is 0, beta hat and E are correlated. That's all I can say. Under E2, which gives me also a distributional assumption, I can say that beta hat and E are actually independent. Why can I say that?
Beta hat and E, MPN.
Yes. Why?
I knew E was normally distributed, but I guess forgotten that beta hat was normally distributed.
So, right. So we managed to write beta hat and E as P times Y. P is a linear transformation. Y under E2 has normal distribution. So by affine transformation property of MBN, this is gonna have an MBN distribution. So they're jointly normal. So having cross covariance 0 means they're independent. Okay, so that's the key point. Under E2, Y is normal, and beta hat is PY. So they're jointly you can say jointly MVN. It means that the vector itself as a whole has a multivariate normal distribution. It's an affine image of a multivariate normal, so it's multivariate normal by vector 4. So the cross covariance block is 0. So by the MVN property that uncorrelated, this is equivalent to independence. Again, vector 4, beta hat and E are independent. Okay. Why this matters? What is a quantity of interest that's built out of the residuals? Besides beta hat, or the beta, which was the parameter, what else do we estimate? Yes. Mean squared error. Mean squared error of what? Mean squared. Okay, that's a complicated thing. So we haven't gotten that far. So but we did compute. Yes.
The residual sums.
Okay, is that the same thing as what? Okay, residual sum of squares. Okay. Okay, mean squared error would be that divided by the total number, which is the guy is divided by n or something. So yeah, so but that is not again something that we discussed yet. So what did we discuss? So we estimated a particular parameter last time. It's very much related to the SSE or the mean squared error.
The least square.
The
Least square.
least squares was like the procedure we used to estimate beta. But we had two parameters, beta and there's another unknown parameter in the model. Sigma squared, yes. S squared, okay, yes. So we did S squared, which was the residual, this is the residual sum of squares divided by n minus p plus 1. Okay. That is our estimate of the noise variance. That's the estimate of sigma. And as you can see, it's purely a function of the residual. Okay. And the fact, interesting facts from probability, this is probably besides the idea of cross covariance, which we fleshed out. This is the new thing probably you haven't seen, or maybe you've seen it in a probability course. When I have two vectors that are independent, or two random variables that are independent, any function of one is also independent of any function of the other one. Okay, so this is a nonlinear function of E, but any function of E would be independent of beta hat, because E is independent of beta hat, so S squared is going to be independent of beta hat. So this strong property only holds for independence, not uncorrelatedness. So I can't say that necessarily this is uncorrelated from beta hat. It may not be. But once I establish independence, then independence basically, let's say, percolates to anything that you build out of these. So that's the key property. So once I have this, then I can build t-tests, because they're built out of beta hat and a squared, and I can do f-tests as well. They're built out of these two estimators, and these pieces are independent, and I can determine the distribution of the ratios and other stuff. So this is a key important fact which follows from that MBN property, and it all follows from the geometric structure of the problem, because this turned out to be zero by the geometry of the problem. That cross covariance being zero implies uncorrelatedness, implies independence under the normal assumption, and then implies that S squared is independent of beta hat. So if you follow the chain of thought, you can see like how geometry kind of and statistical properties kind of merge into this very interesting fact. Sounds good? Questions? I still have one more piece of information, despite moving fast. I think we are a little bit short of time, so I'm going to move on to this. So this is the new thing that I actually wanted to talk about today. What is the distribution of this S squared? Okay, so we have determined the distribution of all the quantities of interest beta hat E and any combinations mu hat. You can build anything out of these as long as it's linear in Y, then you know its properties. The unfortunate thing is that this is not linear. So it's non-linear function of E. E happens to be a linear function of Y, but S squared would be a non-linear function of Y. So that's what I want to talk about. The fortunate thing is that it's not a too complicated function, like it's a quadratic function. It's like one step above linear, and you can determine its distribution, for which I have to remind you what a chi-square distribution is. Okay, so how many people think chi-square distribution? Okay, what is a chi-square distribution?
Given whole distribution, standard squared.
Yes, so a little bit more precisely, if you have a sequence V1 up to VR of standard normal variables that are independent, then I form the sum of their squares that would have a chi-square distribution. Okay. So now, if you want to be working in the language of the course, I'm going to put these vectors like into a vector Z1 up to ZR, i.e. standard normal. I'm going to form a vector Z, and then I'm going to ask you what is the distribution of this vector. If I call this Z. So that's the definition that you see. Often I want to give you like a vector form of the same definition. What will be the distribution? Yes. Normal, multivariate normal. Width. It's a vector, so it has multivariate normal distribution width.
Zero. Mean
Mean zero.
and standard deviation or standard covariance matrix of 1 on the diagonals and then 0 everywhere else.
Yes, so identity. That would be the description of the identity. Okay. Want to say something? Yes. Okay. So that's that. So what this result is saying is that if Z has, let's call this a standard Gaussian vector or normal vector, then the norm of Z squared is chi squared, r degrees of freedom. The norm of Z squared as a vector is the sum of the squares of the elements. Okay, so if you have a standard multivariate normal random vector, if you take the norm squared, it would be chi squared. That's the way that we could write in the notation that we introduced in this course. Now, what I want to do is I want to do a little bit more. So this is the standard thing. I just want to say that, let's say I have a now vector it's going to be equal as y. Normal mean 0 and for its identity, I have an orthogonal projection matrix P. It could be, for example, H in our case. I'm going to call it P, but it's really going to be H for us. And so I'm going to form P times Y and then the squared, like the norm. Look at the squared norm. Norm squared, let's say. And the idea is that this is going to be chi-squared with the degrees of freedom being the rank of the projection matrix. Okay, so this result will be a special case where the projection is just the identity matrix. And it would have rank, full rank, so this is more general. So P is a projection matrix of rank R. I apply P to Y. Y has a standard multivariate normal rank, again, distribution, which means this, like mean is 0, covariance is identity. And so Py norm squared is going to have a chi-squared distribution with R degrees of freedom. And this expression is also equivalent to Y transpose Py. I let you, in the interest of time, I'm not going to do it. It's just do it yourself. Just the properties of projection, you can show it. And this is really called the quadratic form in Y. So that's why this is a result about quadratic forms in Y. The proof, let's do the proof. So how do we prove this result? This part. Anyone has a starting point for this proof? I have an orthogonal projection matrix. It's symmetric and idempotent. Yes.
So, expanding P,
How do we expand P?
to XT.
We don't have that expansion. So this is a general orthogonal projection matrix. Right. So there's no X, let's say. Abstract orthogonal projection. Yes.
Define some Z, like Z times Y for some matrix.
Well, what is U? Right, but starting point is P. I have a symmetric matrix. What is the first thing that you do if you have a symmetric matrix if you run out of options?
Big lambda and
Great. Yes, you do the spectral decomposition. This tells you anything you want, most likely about it. Spectral decomposition or eigenvalue decomposition. That's usually a good start. So P is U lambda U transpose. U is an orthogonal matrix. Columns are eigenvectors. Lambda diagonals are the eigenvalues. Okay, I'm going to do it. And then I have, so Py norm squared is really U lambda U transpose Y norm squared. Here simplification happens because U is orthogonal. There's this little fact that you can check. If I have an orthogonal matrix U, apply it to a vector X, take the norm, what would it be? Normal X. Why?
U doesn't use them.
Yes, so that's what the statement's saying, but if you want to prove it, you square both sides, you get X transpose U transpose UX. And U transpose U is identity, you get this equal to X transpose X. Okay, it shows that orthogonal transformations do not change length. It's a very simple like calculation from the properties of orthogonal transformation. So it means that when I have a U here, I can just drop this U. I'm just gonna add U, like lambda U transpose Y. Because this, you can think of it as just some X. Okay. I'll do it as an exercise. This is kind of a good exercise in properties of orthogonal transformations. So I'm going to call this vector Z. Now we have that transformation that you're looking for. So Z is U transpose Y. What can I say about the distribution of this vector? Yes.
So, and 0 is the mean, then it's U transpose, and then the identity, and then U.
Yes, U transpose the covariance of I, which is the identity, and then U. Right, that's the property. So it's a affine transformation is really a linear transformation of Y. Y has a multivariate normal distribution. Mean is going to be 0. This is that property of covariance that we talked about incessantly. So U transpose I and U. So what is U transpose I and U? Yes. just identity. So in you can just drop, and then you transpose your second identity. So this is a very interesting result. It says that Z is just, again, a standard normal random vector. So Z is highly correlated with Y. You can prove that they're not uncorrelated. So exercise show that covariance of Y and Z is not 0. They're highly correlated, and they're not independent because they're multi-normal. But they have the same marginal distribution. So Y and Z have the same distribution. So orthogonal transformation, kind of rotation and reflection, doesn't change this guy. This is symmetric. Distribution is symmetric kind of around the origin. So anyways, so I get this, which simplifies a lot because lambda, so what are the elements of lambda? What do we know about the diagonal ones? Yes.
They're just eigenvalues.
Their eigenvalues, they're greater than or equal to 0, but we know more about them because it's a projection matrix. What do we know? Yes. Maybe you can go yourself. Remember?
Like they're scaling multiples.
That's what that's what they do. So they scale like once you go to the basis of eigenvectors, that's how they scale vectors. But what are the eigenvalues themselves? We know very much everything about the eigenvalues. Anyone wants to? Yeah. They're just zeros and ones. And so you have how many zeros? How many ones? Number of non-zeros, number of ones would be the rank. So you have R ones and the rest are 0. You have R ones on the diagonal. I can just order them by size. So the first R I'm going to write as 1, and the rest is 0, and then the columns of hue match in order. So what happens when we do multiply by lambda by Z? Like, if you have a diagonal matrix like this, multiply by Z, what would you get? You get Z1, Z2 up to ZR, and then the rest would be 0. So do it multiplication. So this kind of shows that you kill these directions. So the top R are the directions that are kept. And then this is like n minus R directions are set to 0. If you go back to the definition, or like what this means, U transpose Y is basically changing Y into the basis. Like these are the coefficients of Y in the basis of the eigenvectors. And what this is saying is that multiplying by lambda, we are just scaling those directions. So projection matrix doesn't scale the directions that it preserves. It just keeps them, and then the rest of the direction is set to 0. And you can easily see like the notion of degrees of freedom. So the top R is just, they're varying, the rest are always 0. So it really has R degrees of variation. And so the norm of this is going to be just, although Z has n coordinates, the norm of this is going to be just Zi squared, I from 1 to R. And because Z is like these, the coordinates are really IID standard normal. So this is really going to be I squared R. Okay. So again, geometric picture is telling you this is like projecting onto the top R eigenvectors and then setting everything else to 0. Again, we're almost out of time. I'm just having one more slide and then we're done. So this is the proof. Okay, just combines nicely the spectral decomposition, the properties of multi-normal distribution, what the P is doing to like eigendirections, and the notion of degrees of freedom. So why this is useful now? So if you look at under E2, we have the error is like normal with mean 0 and minus sigma squared and IN. If I divide by sigma, I get normal 0 IN. So epsilon over sigma is the standard normal random vector. E is I minus h times y. I plug in, here would be like basically x beta plus epsilon or mu. I minus h kills mu, I get I minus h times epsilon. So really E is a projection matrix times epsilon. Okay, so E divided by sigma is going to be I minus H times epsilon over sigma. This is really that T that we have. This is playing the role of Y in that proposition. So the norm of E over sigma squared is going to be chi squared with the rank of I minus H. I minus H is a projection matrix. So what is the rank of I minus H in the regression context? So it's projecting onto the orthogonal complement of image. So the image of X has dimension T plus 1 under the X1 assumption. So the dimension of the orthogonal complement would be, yes,
And minus only p.
n minus p plus 1 because the fullest space is n dimensional. So the rank is going to be exactly n minus p plus 1. And so what we showed is that expectation of this divided by sigma squared is chi squared with n minus p plus 1 degrees of freedom. In particular, the expectation of this guy is the same as the expectation of chi squared n minus p plus 1. So what is the expectation of chi squared n minus p plus 1 degrees of freedom? Yes. Yeah, it's just n minus from the definition. And so this is showing that the expectation of really this divided by n minus p plus 1 is really sigma squared. If you rearrange this whole sigma squared to the other side and the side. So this is r s squared. So you can see it's unbiased for sigma squared. Okay. So it's unbiased, and we also have the distribution kind of this result. Okay, so that's kind of all I wanted to talk about. And then there are 2 slides summarizing this, so I'm going to post it. And then later, after the midterm, we come back and do the F test and prove this and confident. Thanks. Good luck on the midterm, and I'm going to see you next week.